Okay, everybody. Welcome. Good afternoon and welcome to this special presentation by the Idaho Museum of Mining and Geology. I'm Steve Cox, Museum President. I'm pleased to welcome back Dr. Terry Panhorst as our speaker today. Terry's been very generous over the years in his efforts to bring geologic education to us with his extensive mineral series in the Bonanza newsletter, multiple field trips, and of course, many lectures. Terry got his bachelor's and master's degrees in geology and went into the gold patch, where he worked for a number of years as a geologist and mine manager. Then he got the academic bug, got his doctorate, and became a professor of geology at the University of Mississippi. Please give Terry Panhorst a welcome.
Thank you all for showing up on such a fine Sunday morning or Sunday afternoon, actually. So I appreciate you all spending time trying to learn a little bit about probably one of the groups of rocks anyway, if not the group of rock that I consider one of my favorites. That's a question that kids love to answer, what's your favorite rock? I don't know if I really have a favorite rock, but if I had a favorite rock group, besides musicians, I think pegmatites would probably be it, just because they're really pretty cool to see. Okay, so what I'm going to do is go through a bunch of background information on what pegmatites are, how we identify them, how they're classified, how they form, stuff like that, and then we'll look at some specific examples to show you a better appreciation of these critters. Okay, now pegmatite itself, or pegmatites, are fundamentally basically igneous, although they can be metamorphic bodies, rock bodies. And what characterizes them is that at least part of them are very coarse-grained. In other words, very large crystals. Some of the largest crystals we know of in existence. How frequently people ask, well, how big are they? It runs anywhere from the size of your thumbnail to the size of your fist to the size of the chair you're sitting in to this room. Okay, or anything in between. They can easily be. I've heard of reports, although I haven't seen them physically, of crystals the size of this building that were being actively mined. So anyway, it's that very coarse grain that really makes them characteristic. Okay. Now, the minerals that we find in there, by and large, just reflect the minerals that are found in the rocks surrounding it. Okay, so ordinary igneous minerals that you're gonna have a chance to look at on the back table. These are commonplace minerals that you find in granite all the time. All right, it's just that under certain circumstances, you get an opportunity to grow these crystals very large. It's that grain size, that extreme grain size, is what really makes the characteristic and interesting features. Okay, this is an example of one from the Keystone District in South Dakota. I'm going to be talking a lot more about that because I spent some time doing stuff up there. But here we've got a good example, rock hammer for scale, as usual. Large block of potassium feldspar right there. Another big chunk of feldspar here. You can see the quartz running through like that. And these really big, shiny flakes of muscovite. Really easy to see. All right, and you'll see all of these minerals on the table back there because they're fairly common in pegmatites. Just very large size.
Terry?
Yes.
You mentioned that, there could be igneous or metamorphic, but you don't see, at least around here, you don't see a lot of mafic minerals in there. Dark, it's mostly light.
Yeah.
Quartz. So
this area, yes.
Is it just this area? Others will be full of a lot of darker minerals?
Not necessarily. It just depends. We'll get a bit more into that. Okay. They're also found wherever you find granites, all over the place. This is just an example I pulled out of a publication from back in the early 50s, where they were looking at pegmatite districts in the southeastern United States. So it runs, these large districts run anywhere from Alabama on the west side, running northeast up to into Virginia. And then if you were to look at the northeast, they would have a whole set of districts up there. The west is filled with these pegmatite districts. So they're not uncommon in that sense. Wherever you find granitic rocks, you tend to find pegmatites pretty readily. Okay. Now, some of the pegmatites can be of commercial interest to us. In other words, there's enough there that you can go in and mine some of the minerals coming from there. Now, they're composed. These types of pegmatites are composed mostly of feldspars. A lot of it is potassium feldspar, like the ones on the table back there. A few other feldspars do occur, but basically the feldspars, high purity quartz, which can be important, and then the two mica minerals, muscovite and biotite. Those two, those are the common ones. Those are what you're going to see. Basically, that's the crew you're going to see in pegmatites in the Boise area. You have to go substantially outside of that before you get other things coming in. Okay, another example, maybe to give you an idea of size here. This is some quartz that grew in alongside a beryl crystal from this pegmatite mine in South Dakota. And you can see some of the striations from the outside of the beryl crystal, which they were mining particularly for beryl at this location. And so that's been removed, but the whole back side of the thing is just coated with very large crystals of quartz. Okay, so these are some of the common ones that you see in this area. Some pegmatites, however, have a collection of far less common minerals. That's where some of the economics come in, and that's particularly people interested in mineral collecting. That's where they sort of get into also. Okay, so what do we derive out of pegmatites in an economic sense? Well, one thing that we get is feldspar. Feldspar is used as an additive, commonly in glass or ceramic materials. Changes the properties, maybe a coloration, maybe it's an optical property in particular glasses. It's used for that. The micas, in particular muscovite, although to some degree you also get it with biotite. The micas, it actually comes in two different flavors, shall we say. Here's some fragments of muscovite. A couple of those are actually sitting on the back table right now, so you can see these large, what are often referred to as books of muscovite mica. All right. If the sheets are large, you can use them in specialized applications for electronics, because actually muscovite is fairly insulating in terms of electrical charge. It won't transmit electrical charge. And so it has some use in that aspect. Ground mica is often used as an additive to things like paints and plastics, rubber, material like that, because the sheets of mica are very strong. You can't really, it's hard to pull them apart. You can flip those, and peel those little sheets one from the other, but taking a sheet and trying to rip it apart, it's really hard to do. And so I added, for instance, like paints. If you add some of this ground mica, very, very fine powdered mica in there, when the paint dries, all right, it helps prevent cracking of the paint because of these strong little sheets of mica that are in there sort of holding everything together. So it provides, certain characteristics like that, which are useful. You can find gem quality material in some pegmatites. Typically, beryl and tourmaline are the two big players. There's a slew of other minerals that are found in there, but not nearly as commonly as the beryl and tourmaline. When you go to the mineral show here in February, if you all have attended in the past, you see there is a lot of nice big tourmaline crystals sitting around, and sometimes it's beryl, a few of these others. Inevitably, those come from pegmatites. It may not say it, and it may not be combined with a bunch of other minerals, so it's easy to identify it is from a pegmatite, but typically that's where you get those nice, big, valuable crystals like that. That's where they originated. Okay, uranium, which is kind of a curious thing, but it's a few pegmatites did carry significant amounts of uranium. This was recovered mostly during the 1950s, during our first really big uranium boom in this country, when they were looking for radioactive materials for nuclear weapons, basically, at the time. And pegmatites were easily identified. Anybody with a Geiger counter at the time could run around and find it. And there were a few pegmatites, notably a couple in Colorado, for instance, that produced a lot of uranium, very high grade type of feature. And then you get an assortment of other elements that can be recovered out of some of the minerals that we find in these rock bodies. Everything from, sorry for the abbreviations here if you're not that familiar with chemistry, but it just makes it a lot easier. Lithium, okay, tin, tungsten, thorium, which is another radioactive mineral, and then beryllium, rubidium, and tantalum. A lot of these things have been historically produced from pegmatites. The ones that are underlined, the reason I underline those is all of those elements are currently listed on the U.S. Geological Survey's list of critical materials or critical minerals. So all of a sudden, bingo, there's a newfound interest in locating pegmatites for some of the same. In particular, lithium is a hot commodity because of the mineral spodumene. There's a couple of specimens of spodumene on the back table there that have been historically been a source of lithium. It's not the only source, and it's not the biggest source by any means. But there's a lot of companies out there that are actively exploring for these rock bodies to see if they can find enough spodumene to warrant mining. Okay, let's take a look next at some of the funny shapes that you get with pegmatites. Now, by and large, most of them are formed in this elongate, sort of like dike-like, or think of it as a lens shape form. The vast majority of them, that's how they occur. And we'll see a lot of pictures of that as we go along here. This is a couple of mapped examples of pegmatite, and it's this elongate form. That's real common to see in pegmatites. That's the standard way you see them. Although sometimes they can take on some pretty funny shapes. And the reason for that is that because of the way they crystallize, they take over and make use of cracks in the existing rock, in the granite. And so they have to kind of wiggle their way in however they can in order to grow. And so some of these things, I have a few of my favorites here. The caterpillar model, shall I say? It looks like we've got a bunch of little legs coming out of there. The squash spider is another individual that looks kind of funny there. And this guy, you can describe him however you want. It's just very convoluted in place. And so they can have some unusual shapes. Most of them are elongate in some fashion. Most of them are relatively small. Now, what do I mean by small? Okay, well, lengthwise, it may be just a couple feet or a few feet, less than 10 feet, up to many thousands of feet in length. So that's the range. Okay. Width-wise, if one's only a few feet long, it's probably only going to be an inch or two thick, wide. All right. Whereas a much longer one is going to be wider. So it'll run anywhere from maybe an inch or just a few inches up to, you could have it up to 1,000 feet in width. Now that's a really big baby.
So they follow the fissures, in other words.
Right. Yeah. Yeah, exactly. Okay. This is an example of some of the shapes that you get. And I know you can't read the diagram, the names or anything like there. Here's what's important. Okay, there's your scale. These are all to the same scale. So there's 600 feet in length on that bar. And the majority of these things have this elongate, lensoid maybe shape, map shape to them. Some are rather thick, kind of a fat one there. Many are very narrow, like that fella over there. But that gives you a range or an idea of the different shapes and some of the sizes that these things can be found in. All of these now, to some degree, were economically important. And so that's why they have a lot of detailed information about them. Okay, anybody been to the, you have, very good, to the Black Canyon of the Gunnison? Yeah, that one wall, the back wall there is like 2,500 feet high, huge thing. And it's got these, metamorphics that are just shot through with these pegmatite dikes. Rather striking sort of appearance to it. Okay, now let's talk really briefly also about classification. We're geologists. We like to classify things, right? So you got to have a classification system. What I'm going to introduce here is something that's fairly simple. It's either this or that. Okay, we'll keep it very binary. All right. The classification is based on not only the mineralogy, but also the internal zoning. If it's zoned in some way or if it's fairly homogeneous all the way across or throughout the pegmatite. All right, that's sort of a simple criteria to use. So the homogeneous ones, or think of them as simple pegmatites. All right, these are the ones that are completely unzoned, which by that I mean there's basically no change in the mineralogy from the outer edges of the pegmatite body to the center. That's how they grow. They grow from the outer edges inward. And so there's really no change in the mineralogy that we see. There may be a change in crystal size, but no change in mineralogy. Okay, these type of simple ones make up the vast majority of pegmatites that you'll see. The ones in this area that are so common that we see. Those are all basically of this variety. Okay. Caught this on a trip the wife and I made up into the outside of Stanley, up into the Sawtooth area. And you can see on this largest block here, it's just shot through with these little narrow zones, a few inches wide. Those are all little pegmatite zones. You go up here and look at it, and yeah, it's got a little quartz in there. It'll have a little feldspar, maybe a little mica with it, but it's just shot through. Relatively simple. These are the common ones. As you can tell by the size, that would not be economic by any means. But still, they're of interest to us. Very simple mineralogy. You're talking quartz, you're talking feldspar, primarily potassium feldspar, as I mentioned, and then the two micas. Those are your four big players, and virtually all pegmatites that we're going to be looking at today. Okay, basically, just to reemphasize, little economic value here in that style. They're very common. You see them, once you realize what they are, you see them everywhere. Drive up the Bogus, on the road up there, you can see little examples of it in some of the road cuts, as well as at Bogus Basin itself. Okay, let's take a look at the heterogeneous pegmatites. These are the ones that are a little bit more complex, and that's what some people call these as a complex pegmatite, because they show zoning. People have worked out the sequence of the zones. I'm not going to go through that. If you're really interested in it, there's a whole bunch of publications out there on the exact sequence that you get in there. But just keep in mind, there's a distinct zoning that we see. And the zoning is defined not only by the crystal size, but also by the mineralogy. So the mineralogy changes from relatively simple, small crystals on the outer portion of the body. As it moves into the center, you can have a slew of all kinds of crazy things. And in general, those crystals are much larger as you move in there. Okay, mineralogically it can be very complex. It'll still have the basic four that we talked about, but then there will be a bunch of other things in there too, which is where the mineral collectors and the economic people get more interested in it. Significant economic potential in some of them, and they've been exploited for 150 years easily for that economic potential for the micas and for some of the other minerals that are present in there. Okay, now I mentioned this before, but I want to emphasize these things grow from the outer portion inward. So the last thing to crystallize is in the core of the system. The first thing to crystallize is on the outer boundaries. For a while, geologists kind of thought, well, because of the zoning and they're so different that they must have formed in stages where you had one formed here, and then you had another source of material coming into that opening and filling in the next one. But we've done enough work on it to realize now it's all kind of like a single event as it forms. Okay, a very cartoonish, simplified version, three-dimensional block example of an idealized pegmatite body. But particularly on the lower one here, in this lower slice, the representation is you're getting a change in the mineralogy and the texture as you move from this outer surface here to the inner core. And that's what it's referred to. So think of it as an apple, where you got a rind. Stuff on the rind's not too interesting. You got the core. Well, actually, in most of these types of pegmatites, that's solid quartz. That's all it is, just big, pumping solid quartz. It's the stuff it's the meat of the apple between the seeds and the rind that really can be of importance to us. Okay, now I'm going to talk a little bit about the occurrence of pegmatites in particular. They typically form in fairly deep environments. By deep, I mean at a minimum 2 to 5 mile depth, often deeper than that. Okay, so it's not something that's going to be forming later, like a lot of veins do, associated with intrusives that carry other metals. These things form basically in the process of the granite crystallizing. And we'll get into sort of how that is working here in a bit. The majority of pegmatites that we find tend to form around the boundary of the granite body, particularly the top or the cap. If you think about a granite intrusion that's sitting at depth in the upper part, and then also into the metamorphic rocks that surround that granite. That's where we see them forming, because that's the conditions in which they need you to have in order to form that. Okay, so I love cartoons. Here's another good cartoon. Okay, all the white here all represents our metamorphic rock that's been intruded by this big piece of granite right here. That plug of magma comes in, intrudes, and it's going to stop there and begin crystallizing. All right, the pegmatites that we see, if you're going to find pegmatites in this granite, and Typically pegmatite or granites will have pegmatites in them. It's going to be in the upper boundary of the pluton itself, and also then in the metamorphics around it. That's where we get a lot of the smaller bodies in that area. So that's the most common place that we see them. Okay, so how do they form? Why really are they forming? So what I want to do is to present sort of a conceptual model of how we think they form. And so you got to start with a box, all right? Okay, what is this box? This box is a magma chamber. Looks like a magma chamber, doesn't it? No, it doesn't. But this is the simplicity of it, all right? This is a magma chamber, and we're going to crystallize, or at least start the crystallization process and take it through a big sequence here. Okay, now, we got to populate this magma chamber with stuff. So we're going to have yellow dots and blue dots, all right? Size means nothing here. I just, to make them different, to stand out in contrast to each other. And then we've got this little funny block down here, which actually represents the solid. So that's where we're actually growing granite. That's solid granite down there. Now, I'm not saying that it always forms at the bottom of the magma chamber or anything like that. It's just a convenient place to stick it. So we're just going to put it there. This is going to expand over time. That's going to become less and less. Now, what are the meaning of the dots? Okay, notice there's a lot more blue ones than there are the yellow ones. Okay, the blue ones represent your common elements that we find in a granitic magma. In particular, oxygen, silicon, and aluminum are the big players that you see. That's why feldspars are built out of this stuff. That's why quartz is built out of this stuff. And the mica is built out of this stuff. Okay, these are the common ones that we see in every granite, the magma. They're present there. Now, the yellow ones try to capture the idea that we've got some unusual stuff in there. Okay, much more rare. It's present, but it's not nearly as the abundance that we have in the more common group here. Stuff like water in the form of steam, but nonetheless, there's water in all magmas. All right, and then those elements that we talked about before, lithium, beryllium, all that kind of stuff. Why do we segregate them this way? Because this stuff over on this side doesn't get involved in making feldspars and quartz and the mica minerals. Because in general, they're kind of odd shaped. They're big frequently. And they won't fit into the crystalline structure of, say, your typical feldspar. Sometimes they do. You can find real low-level traces of them in there, but by and large, they don't do a whole lot in there. They're not allowed in. You know, they try to get in there and no, get away. So they get segregated. They stay in the remaining magma. Okay, so what's going to happen if we take this model, this magma chamber now, and cool this off? Well, if we do that, what happens is that we get a lot more solid down here because we've now formed a lot more true granite. We're starting to use up an awful lot of the blue balls here, but the yellow ones, the rarer stuff, isn't being included in that. So it's getting pushed back into the magma. And if this goes over time, you begin to really concentrate these types of materials, which are really rich in water and these other elements that won't fit in. And then, you can take it all the way to the extreme if you want. When it gets down to the end, what you've got is, it is technically magma, but it's very water rich, which is unusual for magmas. And it's got a bunch of funny elements that we don't tend to associate with granite. That is what's going to be forming our pegmatites. Okay, so the idea here is that we're enriching the remaining types, the remaining magma that's in there while the thing is crystallizing. We're segregating those things that don't fit out into the last remaining little bit of liquid that's in there. Okay, now, how do they actually grow? Okay, and this is where it gets to be a little bit of a challenge because grain size is very misleading. Some of you are probably familiar with the concept that if you have a real fine-grained igneous rock, that means it's cooled very rapidly. And something like a granite, which has much larger crystals, it cooled very, very slowly, right? Big difference in time. And so if you take that idea and logically extend it, you say, whoa, we got these things over here which have these huge crystals. And if you do the calculations, back of the envelope kinds of calculations, you find out the amount of time it would take to grow these crystals is longer than the Earth has been in existence.
Exactly.
So clearly, so clearly that can't happen. That's not what's going on. It's not just that they've had an enormous amount of time to grow. So there has to be other factors in there. Okay. These crystals, these very large crystals, probably formed about as fast as everything else coming out of that magma. Okay. They didn't have an extraordinarily long extra period of time. They did what they did in a normal time frame. Okay, and the reason for this is because there are two fundamentally different conditions when they start forming. Okay, first of all, the nucleation sites, which is where you start growing crystals, they're actually probably very few. There's not a lot of them in there. So there's not a lot of places for these crystals to grow. All right, so that's going to limit the number of crystals that are going to grow. Okay, and then you combine that with the fact of something we mentioned before, we've got a very water-rich fluid in there. And so the diffusion of these elements, these ions, these complexes in that water-rich fluid is actually fairly rapid. So they can move pretty easily. You take a typical magma and you try to move ions through that magma, they move real slow. It's really sluggish. Okay, because it's more like syrup or even thicker than that, far thicker than that. So it's hard for stuff to move around. When you get down to the end, it's actually fairly easy for stuff to move around. Okay, so that allows you got a few very large crystals to grow in a fairly rapid period of time. Right at the last, right as the granite itself is crystallizing. Okay, so hopefully that's a little bit of a background on how these things form. I want to look at a couple of examples here, some that I'm familiar with from South Dakota, and at the end, then we'll talk briefly about pegmatites in Idaho. Okay, in particular in South Dakota, you find them in what's called the Black Hills. Now, if you're not familiar with the Black Hills, it kind of straddles the state boundaries between South Dakota and Wyoming. All right. Think Mount Rushmore, that area. Okay. And I included this to show you that actually the Black Hills stands out in relief quite a bit of far piece there from the rest of the Rocky Mountains. And yet it formed at the same time as this stuff did over here. Think of it as a wrinkle in the crust. It was just the furthest east wrinkle that formed at that time. So it shares a lot of characteristics of some of this stuff further to the west. It's kind of out there on its own. Okay, a bit of a very simplified map looking at the Black Hills. What you've got in the center is the oldest stuff, this so-called central crystalline area, which is mostly metamorphics with a bit of granite. And then surrounding that, then you have progressively younger sedimentary rocks. And this formed actually after all of these surrounding sedimentary rocks. A lot of them had already been deposited. And so as it wrinkled in, it kind of broke up through the surface and popped this thing open through erosion, so we could get to see the center portion of this. A geologic map illustrates this a little bit better. This is the very old central portion, this Precambrian stuff, mostly metamorphics, a lot of granitics in there, and then progressively younger as you get away from that. If you've been up in the Black Hills, you probably have gone through Rapid City, which sits sort of right on the eastern side of the Precambrian stuff. Okay. You can't go to the Black Hills without seeing Mount Rushmore. How many people have seen Mount Rushmore? Okay, quite a number of you have. That's good. Good place to visit. That's all carved in granite. The Harney Peak granite. This was actually a photograph I took of some of the cut and polished granite that they used in building the visitor center, the new visitor center at there. And you can identify a bunch of the minerals just by looking at it. Everyone else is out on the viewing platform, all taking pictures of the presidents. I'm over here taking a picture of this. You know, that's when they asked me to leave. So I had no sense of humor. Okay, that's all carved in Precambrian age, Harney Peak granite. All right. Now, I wanted to also point out from this view, you can also see these are the metamorphic rocks that are so abundant in that area. In fact, that was kind of helped limit how far down some of the work went on the carving, because this stuff gets really swirly. You can't handle it the way you can the granite up there. But even if you have not been to Mount Rushmore, just looking at pictures of it, what most people don't realize is that you're also looking at pegmatites. Okay, a good example of that is good old Honest Abe right there. As we look up at him, I've identified several of them. There's a thin pegmatite running up this way, kind of up onto his forehead. Another one cutting through his eyeball here, kind of going up that way. And one of my favorites, which I didn't mark, but when I talk to the kids about this, they always love this, is the snotty nose coming out right there. Another pegmatite zone. Okay, but these are all just examples of pegmatites. Actually, all four presidents up there have pegmatites cutting through their face in some fashion. Mm-hmm. It's in the rock, and so the workers you just had to deal with it. And hopefully it was going to respond like the rest of the rock, which it did primarily. Okay, now, just to show you how abundant pegmatites are in this area of the Black Hills, this represents the Harney Peak granite right there, that pattern. And these contour lines are contour lines not of like elevation, like you might be familiar with on topographic maps. These contour lines represent the number of granitic pegmatites per square mile of that area. So for instance, this hot spot over here down actually southwest of the main Harney Peak exposure, you've got an area down here that has on average over 300 pegmatites per square mile in it. I mean, people have gone in there, mapped them, counted them, and so you could actually put this data together. So this is a very pegmatite-rich area.
Terry, where is Mount Rushmore on that?
Mount Rushmore is actually up in the Harney Peak granite, so it would be sitting kind of up there. It's not too far outside of Keystone. In fact, I identified Keystone because Keystone is one of the old mining areas. If you've gone from Rapid City, drove up through Keystone to get to the monument, you drove right through the heart of the Keystone pegmatite district, and there's a bunch of old mines there. So I'm going to show you one in particular. It's the Etta mine, and I've got at least a couple examples of some of the stuff. The spodumene back there is from the Etta mine in just outside of Keystone. So for scale here, there's 100 feet. This one actually is a lot more oval Well, this lined area here all represents the metamorphic, the surrounding old metamorphic rocks. And then the pegmatite itself is this big, funny looking blob sitting right there. Now they have the pegmatite zones identified. We're not going to go into great detail on that. But just to point out, spodumene shows up in several of those zones. And spodumene was the big player on why they were mining at this location. Now you go and you look at it today, and that's what you got. The center of it is already filled with water. Mining stopped there a long time ago, back in the 60s, I believe. And you can get into there, and that's the access tunnel that on that map was coming in from the southwest. You just walk through this short little tunnel, and it puts you into the main part of where they used to mine. In fact, the tunnel, you can see an extension of the tunnel over here, and then they did a lot of mining out from that. But you've got metamorphics, particularly on the upper right side there, and then some of the granitic with the pegmatite in it on the more on the left side. This is from one of our visits there, Students for Scale. That is a single spodumene crystal. So, pretty good size. They had ones back in the day reported out of there that were 40 feet long. So I mean, that's a big crystal. Yeah.
And why were people mining for spodumene?
Because it's a lithium mineral. It's a lithium silicate. Got some spodumene there. Pick it up. It's curious, kind of a little heavy. It's the white looking stuff. It just looks like feldspar or something. But it's a little heavier than feldspar. Kind of looks like wood. A lot of people describe it as looking wood-like. Good source of lithium right there. Okay, most of the lithium actually occurs in spodumene crystals that look like this. And you can see my hand there as I was trying to photograph and keep the scale all together. But most of them are in these several inch long crystals, okay, that are still in the wall of the old mine. Now, what we're looking at there is actually this portion of the wall. And that little section where my hand was, you could see the sort of the hand-shaped crystal. Okay, that's right there. So my hand basically, kind of filled that right there. So that gives you a sense of how big this is. All the white that you see in there is basically spodumene.
Wow.
So there's still a fair amount in there. Is it enough to turn it into an economic deposit? That's very questionable, but nonetheless, there's still a lot of spodumene, and when you could get access to it, it was a favorite for locals for mineral collecting.
Was there any lepidolite there?
Not there. I have seen lepidolite in other pegmatites, but there really wasn't. There might have been a tiny little amount.
Okay.
But lepidolite is a purple mica. It looks like muscovite,
Yeah.
only has a distinct pink or lilac purple sort of color. There's a piece of it back there from Brazil that I did not collect, but I did acquire. But that gives you a sense of what lepidolite can look like. Now, this was an interesting diagram where what we're looking at here, these fellas that did the work back in the mid-60s, they were looking at the length of spodumene crystals and the corresponding width of the crystals. So basically, you've got a 45-degree angle going up like that. So all your crystals are going to be down in this area. But there were some that were, 6 and 7 feet long. So, you got a spodumene crystal, the size of me. There, whatever, maybe more like that. Anyway, let's not go there. But you can see the majority of the crystals weren't real big. But even at that time, even after mining for 50 years or so, there was still a number of that were several feet long, present in the body itself. Okay, now to finish up, what I'm going to do is just talk a little bit about pegmatites in Idaho. Natural question is, do we have them in Idaho? Simple answer is yes. Okay. So what do we have? Well, basically what you got is a large number of those small, homogeneous, simple pegmatites common throughout the whole Idaho batholith. And if you're familiar with the Idaho batholith, this map should look familiar to you. Boise sits down here. The batholith itself, shown in this red, extends northward to about Riggins and then swings east into Montana. This is traditionally referred to as the Atlanta lobe. And so it's a very, very large intrusive event. Cretaceous age, so it's going back quite a few years into there. It basically forms a lot of the backbone of the mountainous area of Idaho. Okay, so fairly distinct in that sense. Typically within most of the Idaho batholith, this is what you get in terms of pegmatite. They're thin like that, laterally extensive, and they are made up, the crystals are made up of the same stuff you find in the ground. So it's going to be feldspar, quartz, and the two micas that we've been talking about. That's the typical way you find them around here. All right? Now, I found them out if you just hike in the trails around here. I stumble across them every so often, literally stumble across them. Oh, wow, look at that. And I'm watching where I'm going. And then my wife's laughing at me and everything. But, you find these things. If you just went down to the Boise River and spent a bit of time diligently looking over the cobbles that are down there, you probably find occasional cobble of pegmatite, because it just occurs in this area. So they're not unusual. It's just that they're not really abundant, and so we don't pay necessarily a whole lot of attention to them. Now, on top of that, some of the younger, the tertiary age in granite intrusions do host pegmatites that have reportedly produced gem minerals. Okay, examples of these are things like aquamarine, beryl, okay, topaz, fluorite, and a few other minerals. But these are the more common ones that one would find in those locations.
Question.
Yeah.
So for the Idaho pegmatites that we often see stumbling across the trail,
Yes.
where do the rare earth minerals in that magma go if they're not in?
Well, the thinking is that they weren't there to begin with.
Oh,
It was a granite magma, but it was not particularly enriched in those more interesting elements that we might be looking for. So they weren't, if they're not there to begin with, or they're at extremely low levels, we're not really going to see them. So it seems to be there's certain magmas, which is kind of what I was getting into here with the tertiary ones. There's certain magmas which seem to be enriched in these more unusual elements. For what reason? I don't know. Maybe it was some of the stuff the magma was passing through as it was coming up, able to glom up some good stuff in there.
Yeah, Terry, that question that we just heard, I know a lot of times now when you sell a home in Boise, Idaho, you have to have a radon test. So, so is that coming from those, and because we have granites here?
That's coming just from the general granites.
That have that.
That can have that. Yeah. Yeah. I mean, granite, just the granite countertops can have that. Not in a level that would be of any concern, because it's the mass quantity is what you're concerned with. A countertop is thin, there's not enough there. But if you take a large block of granite where you've built your house upon it, and then you build this nice house that's very securely warm, so you seal everything up, right? So the radon, if it works, up through the soil into your house, it can't dissipate. So you can concentrate it in your house. So that's why they're concerned about it potentially doing that. If we lived in old style houses where you didn't even have glass in the windows, like that, that stuff was gone. And so it was never an issue. It was only in the last, century or so when we started building well-insulated homes, did you have the opportunity to start sort of concentrating radon. But that's just a general feature of most granitic rocks, that they have slightly elevated uranium levels, which radon is one of the products of that.
Hey, Terry, you
Yeah.
haven't mentioned apelite dikes. They still use that term?
Yeah.
So what's the definition?
Apelite generally is characterized as more finer grain, kind of sugar grain size dikes of a lot of times feldspars. Yeah, and you find those around here too.
Yeah.
I think they're just not necessarily as interesting. That's why people don't really focus on them.
But it's still kind of the same process happening.
Yeah, very similar, probably very similar process. It's a segregation from the magma. Because the way these things form, they form along cracks in the granite host rock. And so the rock has to be solid in order to form a crack that these last remaining fluids can get up through and grow these crystals. Okay, anyway, tertiary age granites. So here's sort of a map of the lower portion, the Atlanta lobe of the Idaho batholith. I highlighted towns here so you can see that easier, where it's surrounded by. And the black areas here are the tertiary age plutons that were identified at the time of the map anyway, as ones that lower tertiary age. Actually, the reason that these studies were done at the time was because they were trying to see if there was a relationship between like the gold and copper mineralization to the location of these tertiary age plutons. So that was sort of the motivation for putting this together. Now, if you look in the literature, there's not a whole lot of literature on pegmatites within these tertiary age plutons, but there's a little bit in particular about collecting stuff there where minerals have been collected. And it seemed like there's 4 different identified plutons that have reported occurrences of things like the topaz and the beryl and stuff like that in some, not all by any means, but a few of their pegmatite zones. And as you can see them listed here, those 4, there's probably others out there that aren't as well studied, and so they just wouldn't wind up on a little chart like this. But that seemed to be the consensus at the time. Closest one to us is going to be the sawtooth, and it's really the best studied of the ones. A lot more study has gone into that, maybe because it's a little easier access to get in there to see it and find out what's in there. The map from Terry's book, the one we sell here. Okay, for reference, Boise there, you can see Stanley right there. The sawtooth batholith formally, it sits right in that area there. Okay, but the green ones shown in this map are the tertiary age. It's just that the sawtooth, if you want to go collect that kind of pegmatite minerals, that's probably going to be your closest place. Now, you also realize you're going to have to backpack into there because you're in the middle of the sawtooth range. if you don't mind working at 9,000 feet, sleeping out of a tent for a while, might be able to do something. But it's within the recreation area there. So even if you find something, you're not going to be able to mine it because they don't allow that within the recreation area. So. But it's rugged country, but nonetheless, a number of them have been reported from that area. Okay, look at that. It is almost 2 o'clock, which takes me to my last slide. Just a parting shot from the Edamine. This is from 1904 U.S. Geological Survey photo. You can see the old gentleman in there for scale. And beside the gentleman, you also notice these were a couple of spodumene crystals, one there and one right there. And that's what that old timer was in there, helping mine. So it's, they had some pretty serious size to them.
Now, isn't some of these plutons and some of these big pegmatites, aren't they temperature and pressure regulated?
In terms of their formation,
Yeah.
that would play a big role.
I was wondering about that.
Yeah.
Temperature and pressure. Bowen's reaction series always rolls. So it's a...
Well, yeah, to a certain degree. I mean, Bowen's good,
Yeah.
but you have to be careful about pushing it too far.
Exactly.
But it does explain some of the enrichment of the minerals that we see in here. The potassium feldspar and the quartz.
That's right.
And the two micas. That tends to form, the end of Bowen, which you're looking at residual fluids. For those of you who don't know what we're talking about, don't worry. We're wading into the weeds here on stuff we learn.
It was just a comment because I always go by the crystal content, potassium feldspars. And at the end of the Bowen's reaction series, we're not talking about temperature always, but we're talking about the combination of temperature, pressure, in the
Exactly.
reaction.
Yeah, and I think that's probably helps explain a lot of why we find pegmatites in certain areas,
Exactly.
and we really don't find them commonly in other areas. And yet, looking at it, the granite appears to be the same. So there's those little nuances going on during the time of formation that you have to take into consideration that, it's kind of like the old saying with gold is where you find it. Well, pegmatites are kind of that way.
Yeah.
They're where you find them, and that's where they're going to be hanging out. So if you want to find an elephant, you go to elephant country. Okay, yes.
Do you know what it was back then that they were interested in lithium? I mean, today it's apparent why there's a big interest in
Right, yeah, for the batteries.
Right.
But back then it was used for other things. Some medicinal use, which it's still used for, but also then it was used more in additives to glass and other materials that gave the
Some of them are
certain-
semiconductors.
Semiconductors, that's something else that it's used in. Yeah.
So what kind of pegmatites would you find gold in?
Unusual pegmatites. Gold is not a big player in pegmatites. It's not that it's non-existent, but it's just not common. Not like you find gold, say, in epithermal veins and deposits like that. In pegmatites, gold is just not one of those elements that is found there very much. And so there are some examples of where during the process of mining they were able to recover some gold also, but it's not a big one.
So what differentiates an epithermal vein from a pegmatite?
Well, epithermal vein now would form from fluids that are probably being expelled by the granite or by the intrusive body, but they are very water rich, and they also go out into oftentimes the country rock around that, and they seem to pick up stuff there. And so there's a certain philosophy that these fluids can scavenge gold, silver, other metals from some of the surrounding rocks and then form them into these veins. Okay, whereas the pegmatites form certainly at the end or at the last little part of the granite sequence, but they're kind of really inside the granite. They form at a much higher temperature, much greater pressure. Okay, I don't know if that helps an explanation there, but
So wouldn't they both be near the top of the batholith?
well, oftentimes, like with epithermal veins, you don't find them in the batholith. You don't find them related to a batholith at all. You know, you find them what would seem like miles from that source, potential source. So it's a completely different environment in which to form. Those might form much closer to the surface, much lower temperatures, relatively speaking. Other question?
Yeah. Do you know if it's possible or even like economically productive to make certain pegmatites artificially, like in the lab?
No, I can guarantee you it wouldn't be economic.
Okay.
Yeah. No, it's always cheaper to get, you know, your naturally occurring stuff. It's just that you have to have those processes where somehow the naturally occurring material concentrates itself in some fashion. If it were really, you know, to grow them in labs or create them or something like that, you know, all those from element number 93 up through whatever it is now, 125 or something like that, all those man-made elements, there'd be a market for those. We'd be using those. And nobody does that because they're far too expensive.
The half-life is ridiculous.
Yeah. And you can't make enough of it. The trick is you just have to find where you can get enough of it already concentrated.
All right, thank you.
Yeah. That's the whole science of economic geology.
Well, we sort of fulfilled the 1 hour requirement. Terry probably might be able to stay a few minutes and
Oh, yeah.
explain some of the specimens you brought.
Yeah.
Let's give him a big hand, please.